Welcome to Organic Chemistry. In this video, we tackle the last functional group of the year, amines. Let's get started. Before we begin the chemistry, let's place amines in the larger functional group landscape. Amines are lower in IUPAC priority than alcohols, but above alkenes, alkynes, and halides. That means if an amine is the highest priority group present, we name the parent chain with the suffix amine. Mechanistically, though, what matters more is that amines are defined by a localized lone pair on nitrogen. That lone pair is directional and available for bonding, and much less resonance stabilized than amides. So amines tend to be nucleophilic and basic. This makes them very different from nitriles, imines, nitro groups, and azides, even though all of those contain nitrogen. Before extending hydride chemistry to nitrogen-containing groups, let's briefly review the carbonyl case. This slide is a reminder that stronger hydride reagents don't just react faster. They open access to entirely different functional group classes and deeper reductions. Now we extend that same logic to nitrogen-containing functional groups. Here we have amines, oxamines, nitriles, amides, and azides. Amines can be reduced to either primary or secondary amines, depending upon what is attached to the nitrogen. Oxamines always give primary amines, however, because reduction always removes nitrogen and leaves oxygen and leaves nitrogen attached to only one carbon. Nitriles also always give primary amines because the nitrile carbon becomes a methylene carbon attached to NH2. Amides can give either primary or secondary amines depending upon the substitution already present on the nitrogen, because reduction removes oxygen but preserves the carbon-nitrogen framework. Azides give primary amines and expel nitrogen gas, which makes that transformation especially entropically favorable. The unifying rule is that hydride attacks the most electrophilic center. Then heteroatoms such as oxygen or nitrogen are removed as aluminum-bound species. Do not memorize these as isolated tricks. See the pattern. Pi systems are reduced, oxygen can be removed, nitrogen can be expelled when the system allows it. We should also remind you, in terms of reactions that we have previously covered, that catalytic hydrogenation will also reduce nitros, azides, nitriles, and amines to amines. Here we review our mechanistic foundation for reductive amination. A primary amine adds to a carbonyl, proton transfers occur, water is eliminated, and the product is an imine, also called a Schiff base. A secondary amine follows the same early steps, but because there is no nitrogen single bonded to hydrogen left to support amine formation, deprotonation must occur at the alpha carbon instead, leading to an enamine. That is the critical fork in the road. Primary amines and ammonia alone can give imines. And upon this, we combine two ideas. First, the carbonyl reacts with ammonia, or primary amine, to form an imine. Then the imine is reduced with lithium aluminum hydride to give the amine. The important warning on this slide is that this pathway proceeds through an imine, not an enamine. That means the reaction must begin with either ammonia or a primary amine. If you start with a secondary amine, you divert into enamine chemistry, and this specific reduction pathway is no longer viable. Mechanistically, the hydride attacks the electrophilic carbon of the C double bond N, and after workup, the result is the amine. So stepwise reductive amination is really just imine formation followed by imine reduction. Our next refinement is in situ reductive amination, where we do not isolate the imine first. Instead, imine or iminium formation and reduction occur in the same flask under carefully tuned conditions. This is more efficient, but it only works because the reducing agent is selective enough to reduce the iminium species without simply reducing the starting carbonyl. A mild organic acid is used so that some of the imine is protonated to an iminium ion, but the medium cannot be so acidic that the reducing agent is destroyed. Sodium cyanoborohydride is the key reagent because it selectively reduces the iminium, not the carbonyl. That selectivity is the entire reason the one-pot method works. Even though neutral imines are weaker electrophiles than carbonyls, protonated iminium ions are actually more electrophilic than both, and so they become the preferred reduction target. The solvent must not be water, because water drives the equilibrium backward and hydrolyzes the imine. Instead, we use a polar protic organic solvent, such as ethanol. One more subtle point. Under the reaction conditions, the product is often present in its ammonium form, and bicarbonate workup is required to free the neutral amine. So the textbook amine at the end is usually the isolated product after workup, not necessarily the dominant species inside the flask. And now we flip the role of amines. So far, nitrogen has been our target. Now nitrogen can become a tool. Amines can act as nucleophiles, and through exhaustive methylation, they can be converted into quaternary ammonium salts, which are excellent leaving groups. Once that happens, the molecule is primed for elimination. Hofmann elimination begins by treating an amine with excess methyl iodide. Each alkylation step generates an ammonium species. An excess amine deprotonates those intermediates until the fully quaternized ammonium salt is formed. Then, silver oxide in water effectively converts the iodide salt into the hydroxide salt. Upon heating, an E2 elimination occurs. The key result is that Hofmann elimination favors the least substituted alkene, the Hofmann product, rather than the more substituted Zaitsev product. Why? Because the leaving group is bulky and positively charged, so the base removes the most accessible beta hydrogen. This is a geometry controlled anti-periplanar stereospecific E2 process with no rearrangements. The larger lesson is beautiful. The amine is first used as a nucleophile to build a quaternary ammonium ion leaving group, and then that same nitrogen functionality enables elimination to an alkene. Thus, across this amines unit, there are really three big synthetic ideas. First, multiple nitrogen containing functional groups can be reduced right down to amines. Second, carbonyls can be converted into amines through reductive amination, either stepwise or in situ. Third, once amines are present, they can be transformed into quaternary ammonium leaving groups and driven into Hofmann elimination. In other words, amines are not just a functional group to memorize. They are the crossroads between nucleophilicity, basicity, reduction chemistry, and elimination chemistry. Till next time,